In this video, we're going to look at heat capacity. We're going to look at what heat capacity is and then how to do some calculations involving heat capacity. So here's our definition for heat capacity. It's the amount of energy that's measured in joules required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. And we represent it with a lowercase c. And you can see the units based on what we've read in the first bullet point is that we have joules per kilogram dot degree Celsius. And those are listed in our Nelson Physics 11 textbook on page 281. You will be given those values on your quizzes, tests, and your exam. So you just have to go and look them up in that table. So I'm going to be using values that I've looked up in that table when we're doing ours. So to determine the amount of thermal energy transferred from one object to another, we use the formula Q equals mc delta T, where delta T is our change in temperature, so we would be doing T2 minus T1. C is our specific heat capacity, and our mass is our mass in kilograms. So just remember that we need that in kilograms, especially if you're also in the chemistry class. Physics, we need kilograms. And you are going to get positive and negative values, and sometimes your textbook won't actually say that the Q value is negative. It'll just say that a quantity of energy is released. And when you see released, that means your Q is negative. If you see absorbed, your Q is positive. I'm fine if you leave it as a negative value if that's what you get. So here's our first example. How much energy is absorbed by 500 milliliters of water if it's heated from 25 degrees Celsius to 98 degrees Celsius? So the only formula we have is that Q equals mc delta T formula. So it doesn't have volume, and this really is only going to happen with water. If you have 500 milliliters of water, that's 500 grams of water because the density of water is 1 gram per milliliter. So that's actually going to give us our mass of 0.5 kilograms. And then you go and look up the C value, 4.18 times 10 to the power of 3 joules per kilogram dot degrees Celsius. And then we have T1, 25 degrees Celsius, T2, 98 degrees Celsius, and then we can figure out our delta T by doing T2 minus T1. So we would do 98 minus 25, so we get 73 degrees Celsius. So we don't have to rearrange the equation. We can just go ahead and put our information in. I'm not going to put my units just because I'm going to run out of space if I do. You can show unit cancellations here, so it might be helpful for you to show those units and continue practicing solving those. So we get 152,570 joules. Your textbook is going to convert that to kilojoules, so we would divide it by 1,000. And then we want to look at our sig figs. The 500 milliliters, those are those zeros that may or may not be significant. So let's round so that we have 2 significant digits based on our degrees Celsius. So we'll leave it at 150 kilojoules. So let's look at another example. So we have a 1.5 kilogram cast iron griddle is used on the barbecue. It was at a temperature of 175 degrees Celsius and cools to room temperature 25 degrees Celsius. How much energy does it release to its surrounding? So we're trying to figure out Q. We have mass. We have our T1, it's 175. We have our T2, 25. So let's go ahead and figure out our delta T. So we have negative 150 degrees Celsius for our delta T. And then you would go look up your C value in that chart. It's 4.5 times 10 to the power of 2 So times 10 to the power of 2 joules per kilogram dot degrees Celsius. So then our formula, Q equals mc delta T. So I'm not showing you all of the different ways that you can rearrange that formula. That's just all based on your math. So 1.4 kilograms, 4.5 times 10 to the power of 2, negative 150. So Q here is negative 94,500 joules. So we can divide that by 1,000. So we'd have 94.5 kilojoules. And we only want 2 sig figs because of our mass. So let's round that to negative 95 kilojoules. All right, oftentimes these are the types of examples you're going to see. So in this example, we have information for lead and we have information for water. And so to use this formula, we're going to use, or the new formula we're going to use is, hold on, just let me delete that. We're going to do Q released plus Q absorbed equals 0. So we're not really going to worry about which one's releasing energy, which one's absorbing energy. We're just going to write down the information that we have. So we have a mass of lead. We have a T1 for lead. And then it's being placed in water. So remember, if you get a volume of water, it's the same as your mass in grams, which we will then convert to kilograms. And that water has an initial temperature. So I'm just going to go back and put T1 PB there. And T1 H2O is 10 degrees Celsius. And we're told that the specific heat capacity of lead is 1.3 times 10 to the power 2 joules per kilogram dot degrees Celsius. And we know our C for water is 4.18 times 10 to the power of 3 joules per kilogram dot degrees Celsius. So what we're going to do is we are going to, basically, I'm going to change this. We don't care which one's absorbing and which one's releasing. I'm going to put QH2O plus QPB equals 0. So now what we're going to do is we're going to put all of our information for water into this equation, and we're going to put all of our information for lead into that equation. So for our water, we have our mass, we have our C, and then we have T2 minus 10, because that's actually what we're being asked to find. And both the water and the lead are going to have the same T2. Okay, so I'm just going to write down on my other line here. So then I have my mass, I have my C value, and then I have T2 minus 95. And that's still all equal to 0, okay? So now I'm going to simplify. So I'm going to do my 0.3 times my 4.18 times 10 to the power of 3. So we get 65. And then we have T2 minus 10. And then we have plus, and then 0.05 times 1.3. Oh, sorry, just let me delete this. 0.3 times 4.18 times 10 to the power of 3 is 1,254. Sorry about that. And then 0.05 times 1.3, that's our 65. And then I'm going to expand. And then I'm going to do the same here. Then I'm going to collect my like terms. So that's all equal to 0. I've been forgetting to do that. So I'm just going to flip to a new slide just so that we have more space. So I'm just going to write down what we've just finished. So then I'm going to isolate my T2 term because that's what I'm trying to solve for. And when I move my 18,715 over to the other side, it becomes positive. And then, and so then we get T2 equals 14.2 degrees Celsius. So both the water and the lead have that temperature, and we just really want to round that to 2 sig figs, so we'll do 14 degrees Celsius. So that's just a quick review of heat capacity.